Hi, good afternoon. I've been waiting on you. Come on in. So you were saying you had some questions about sequential batch for this stuff. I think I have some information on that. Yep, here we are. All right, folks, so here we are talking about sequential LSDC. And so we're starting a bit of a new and our final conversation for this class. Also, by the way, this was recorded on a Friday, so in keeping with good morale and discipline, I'm in civies. So if you're watching this at some other time, that's why. All right, so what are we talking about here with sequential LSDC? All right, so what we've already done, this isn't a whole new conversation, what we've already done is taken what, 17 observations and used them to get a least squares fit to the best orbit that it actually is. Right? So what if a month later we get a bunch more observations? So that's what we're calling, what we're looking at here. Batch 1 is what you've already processed. Okay, and so that's what I mean by batch, is a set of observations. And then at some other time in the future, all of a sudden, some more stuff rolls in. Okay. So these are some key equations here that we've been using. If we have an A matrix and a B matrix and a weight matrix, then we can get the del x hat, the little step, the change to what we think is a solution that we need to add to our old solution to get a better orbit solution. And that's what we do. We get a new based on the old plus the mathematical delta. And we just keep doing that until the delta pretty much goes away. So how do we handle this situation where we got new observations? So we got so many options. What we'll call option 1 here is keeping the solution from batch 1 and just kind of use that as our guess instead of Herrick-Gibbs. We'll use that as like a really good guess. And then kind of redo the process using site 2 observations. Right. So this isn't that great of a way of doing it, okay? Because if all you do is take your results from batch 1 and use that as your starting point for the batch 2 data, then you've thrown away all the weights, all the covariance, and you're just fitting the new data, basically. So let's say that you had 100 observations in batch 1, and they're all really good from the latest, newest radar site. And then a month later, two observations come in from an Apollo era site out in Australia. So you don't really just want to take a starting guess and fit those two and say that that's such a great answer. All right, option 2. This is probably the one I would do because it seems the most straightforward. Is you have new data. So instead of 17 data points, let's say now you have 17 in batch 1 and 3 in batch 2. Okay, so you could just now say, I'm going to redo the whole problem with 20 data points. That's pretty straightforward, right? You know, the problem is that you're recomputing a lot of stuff that you've already done, those first 17 data points, and these matrices are going to get bigger and bigger and bigger each time you redo it, and now you have 5,000 data points. These matrices get pretty big. All right. So probably the smartest way is to So probably the smartest thing to do is to use the state solution that we had from batch 1 in p hat. I don't think we've used p hat before, but as you'll see in a minute, p is just the covariance matrix, shorthand for that. So if we can use our old answer and all of our old matrices, and then use new site 2 data somehow, and we can combine that without redoing all the old stuff, then that's going to be the smartest way of doing that. All right, so nothing new here with these definitions. We're just making sure that, that we remember them. X hat sub k, k is going to be what we already have, that batch 1 solution. Okay. Now x hat sub k plus new is what we're trying to get. So there's not actually an addition here. It's the old stuff and the new stuff. If we can find that, then that's what we want. And then the B, A, and W sub k, well, that means just batch 1 stuff. And then we'll have some new ones from the new data. Okay. All right, so this is the meaty slide today. What we're going to do is just kind of concatenate our existing B matrix with the new stuff, and same with A. So if you boil this down even simpler, if we just think of the B matrix, hopefully you know by now that's just a big, long column. So what if you, instead of 17 data points that you've already done, what if you had 18? What would have happened? My goodness, well, it would have just been another 3 rows on the end of that column, and another 3 rows on the A matrix. So yeah, we can just take what we have existing A and B matrix, and now take this new data and just grow it towards the bottom. Okay. That's your new information, just going right on the bottom there. Now the weighting matrix, also, it just gets bigger, and we're adding the new weights on the diagonal there. Now this is where the weighting matrix gets kind of interesting, because it could be different sites altogether, and that Apollo era thing in Australia isn't as good, and we don't want to weigh it as heavily. So now, instead of just reading those numbers once and just keep repeating them in a diagonal, we'll have some new numbers to put in here. All right, so this is the existing equation. That's how we define the step in our guess that we want to take. And if we take the new B and A matrix in this sort of concatenated form, and we start plugging it into there, then it looks like this. All right. Then we do some linear algebra here. No new concepts here. We're just doing some linear algebra, and we get this. All right. So now I'm about tired of writing A, W, and B so much. So no big mental breakthroughs here. I'm just going to define my covariance matrix as this and start using that. And so I can invert it if I want. I'm trying to just get this expression rewritten in a little bit better shorthand. All right, and that gets us to, this is the equation we had a second ago, and now I'm using shorthand, and I get this. So when I include new observations, the step for this iteration that I want to take to improve my guess at the COEs is this. So it's using old stuff from the first batch and including new observations. So we have succeeded in incorporating the old state and all of its covariance, A's and B's, information into the solution without reprocessing anything that we did from batch 1. Yes! Now a couple nuances here. This delta that we had before we started looking at batch 2 was pretty much 0, right? Because that was kind of when we stopped iterating, is when we didn't see any more change really. So we could further simplify this by throwing that out. It's pretty much insignificant, but we won't do that right now because this form is something that might come up again later. Right, so the positives with this method is that you can easily reevaluate the new covariance matrix and then go on to site 3 and just, for as long as you want, keep going. And every time you get a new batch and you update this, it keeps all of your covariance matrix and your steps current, up to date. And as you're doing this and you compile it and you get your old information, some of these matrices will be, they won't grow as they would if you just started all over with new information. All right, now the negatives, the covariance matrix might be getting really small. In other words, it's saying you've done a really good job of fitting this, and we got nothing else to add. And so then when you give it some new information, it's not going to be included very well. Now we'll call this that you're being smug. I'm not sure if that's an actual industry term or just a Vergesism, but it actually kind of fits. Because you can imagine that 17 people are on a team and they're comparing notes and they're iterating back and forth for a long time to come up with the best plan. And then 3 new folks show up. They're kind of out of the clique, right? And they may not be fully included as if you just started over with 20 new people trying to come up with a solution. All right. Now the other nuance here is that hopefully this makes some sense, but we didn't really get into like the MATLAB algorithming of exactly how you would implement this. And there's a little bit left to the imagination on that. All right, so some food for thought. Could we use that sequential batch system that we just talked about? Could we get solutions or COEs for a time closer to now, the most recent batch, instead of always coming up with a solution that is at the epoch, which might be 3 years ago, right? And so yes and no. All right, if you get that solution at epoch, which was 3 years ago, and you want the COEs today, then certainly you can use COWL to propagate right to now and get your COEs. But that's only as good as COWL, right? And we know we're not including solar pressure, the moon, all that. The actual solution you are getting is the solution at that epoch, which was probably pretty close to batch 1. Now, could we do this method if new batches were single data points? And if you think about the space station, I see it today, I see it tomorrow, there's 4 days go by, I see it again, then I see it 3 days later. If we count each of those as an observation, then this is actually very typical of the problem we're dealing with, is one observation at a time. And we want to update things as we go. So the answer to this is yes, we can use the system. But you're just adding, if it's only one observation, you're adding 3 rows to the B&A matrix. It just seems like a lot of linear algebra here to just update the whole thing with one data point. But it could work. Now, these are not random questions. This is kind of setting the stage for what we're doing the rest of the semester. Because what we would really like is a system where we collect one observation and then use all the previous observations, all of the numbers we've already crunched, and get the COEs right now, including everything that's happened in the past, not going way back to epoch. And that's what we're gonna do next. Now, the sequential batch, let me be clear, this system that we just went through on how you would do this, we're not going to implement that in MATLAB. Okay? We're going to dig a little deeper to try and get to that holy grail of updating our solution every time a piece of data comes in and updating it to the COEs right now. That's what the next project is going to be about. But this hopefully kind of sets the frame on how we would tackle this and what we're trying to do. All right. So don't forget to hit that like button and subscribe, and see you next time.